Welcome to today's discussion of a new test. Now we're going to look at the chi-square test, which is another test of significance. The chi-square test is sometimes called a test of independence, or as you'll see, there's a few different types of chi-square tests we're going to discuss today. Generally speaking, the chi-square can tell us how does the model fit the facts. The model is usually we're referring to as our chance model, and the chance model is described by the box model that we make. If there are more than two categories, we use the chi-square test rather than the z-test. So that's the big difference here. We could use the z-test when we had just two categories. So we were comparing the frequencies or percentages in two categories. But if we have a categorical variable and there are more than two categories, you need to use the chi-square test rather than the z-test. And chi-square will tell you whether the categories are equally likely. Let's think a little bit about the construction of the chi-square, and this will make sense. So the chi-square uses a similar format to our other tests where we have observed frequencies and expected frequencies. The observed frequencies are based on the chance model, and the expected frequencies are, the expected frequencies are based on the chance model, and the observed frequencies are whatever you observe. So this is just the same as we saw in the z-test, except now we're dealing with more than two groups, three or more categories. And this type of chi-square is often called a goodness of fit. This tells us whether the model or data fits the model expected. Okay. And we don't have to deal with standard errors here. Instead, we just take our observed frequency minus the expected, square it, and divide by the expected frequency. Squaring it helps us to deal with negative values in our observed minus expected. Chi-square gives us a measure of the distance between the observed and expected frequencies. So if the observed frequency is very far from what's expected, then the chi-square value is going to be large. When the observed frequency is close to what you would expect, chi-square is small. You can see here that we have a chi-square distribution. We use degrees of freedom here too. Most tests, I think pretty much all tests, besides the z-test, use degrees of freedom. The z-test doesn't need degrees of freedom because it's based on a normal curve and the sample size is large enough to approximate a population. So we have here an example of the chi-square curves. As you recall from our previous chapter, when you have degrees of freedom, there's technically always a different curve based on the degree of freedom, and the curves better and better approximate the ideal distribution for the statistic as the degrees of freedom increase. In this case, the chi-square curve looks like this solid curve here. This is what the probability distribution for a chi-square statistic looks like. And we will use a similar table to the t-table to look up our chi-square values to help us decide if our p values are equal. So, when we use a chi-square, we're still following the hypothesis testing model, except that now we're just doing a different test. Like before, you will get an observed test statistic, and then your observed test statistic, you can envision it on a distribution. In this case, the chi-square curve, as you can see, it's not normal. It has this skew. And the chi-square values for a goodness of fit test are always plotted on the right. So you plot your value and you read the area from the table. So if this is telling us the cutoff for a p-value of 5%. So if we had 1 degree of freedom, then any value, for example, that is larger, equal to, or larger than 3.84, if we said this was our 5% cutoff for 1 degree of freedom, then the value here would be 3.84. And anything larger than that would be also significant. As you can see, 1% is down, further down, 6.64, okay? And so when you're making decisions here, you just look up your significance value, and you can't get an exact p-value. Just report if it's less than 5% or less than 1%. When should you use the chi-square test as opposed to the z-test? Well, if the data, the chi-square tells us whether the data are like the result of drawing at random from a box. And in this case, it matters how many tickets are in the box. So we use the chi-square test when it matters only how many tickets of each kind are in the box. Conversely, when we use the z-test, or the z-test applies in a context where we have a box whose average is given, and it's only the average of the box that matters. The question is whether the average is the same or different than another average. So a z-test applies in that situation. For example, if you have a similar setup where you draw from replacement with a box of tickets numbered 1 through 6, but we don't know the percentage of the different kinds of tickets, we can test the hypothesis that each value appears equally across the tickets and use the chi-square. We want to know if each ticket is equally represented in the box. And there's only one box that satisfies that hypothesis. The 16.6 is just 100 divided by 6. However, if we test the hypothesis that the average of the box is 3.5, then we use a z-test, and there could be many different boxes that could produce an average of 3.5. The point is that we're either interested in the average, or we could use a z-test. Since this is more than 2 categories, we use a chi-square for our proportions test. The chi-square test has a basic structure where you have the data, which are your number of observations, and for the relative categories, and the chance, that helps direct you to the chance model, where you map out how the data, according to the model, the data would relate, as we saw in our simple 6-ticket box model. We have a frequency table. You have to make the frequency table when you do the chi-square statistic, so you can get the expected frequencies, which would be equal across groups, or the observed frequencies, which you get from the basic data by counting. The chi-square statistic is computed from the formula we saw before, and our degrees of freedom are always 1 less than the number of terms in the sum for chi-square. And our observed significance level, as we saw, is the area to the right of the chi-square statistic under the curve based on the degrees of freedom. So you can just make that decision using the significance table. There are a variety of ways to apply the chi-square. One interesting way, how Fisher used the chi-square. He estimated that, or excuse me, he found that Mendel's data, which we skipped over chapter 25, but Mendel, you might recall from biology, did the testing, did various genetic experiments involving plants. And Fisher used the chi-square to show that Mendel's data was fudged. For each of Mendel's experiments, Fisher computed a chi-square statistic. The experiments were all independent, so Fisher was able to pool the results. And when he did this chi-square, he was looking at the chance model, he wasn't looking at the chance model for the individual experiments. He was comparing the hypotheses. So the null hypothesis was that Mendel's data were gathered honestly, and the alternative hypothesis was that Mendel's data were fudged to make the reported frequencies closer to expected values. Since we know that small values of chi-square argue against the null hypothesis, in this case, we compute P as the left-hand tail area, and the rest of the process is the same. So we just look at when we were looking at our curve, the left-hand side is over here, and this would be, we only have this 90% cut off on the table here, but 90% is on this side. So this would be the 10% area in the left tail. If that makes sense. So by the way, Fisher did find that it was that Mendel's data was fudged. It was very unlikely that the results were always so similar. So that's what the test in that case told us, was that the results were too similar because we were testing the null hypothesis. So just another important application of the chi-square test. You can see that you do see this kind of application in the pooling of values, sometimes in meta-analysis articles. And another important use of the chi-square statistic is the test for independence among nominal variables. In this case, we are just setting up our chi-square statistic so that on the null hypothesis, the differences in the sample just reflect chance variation, as always in the null hypothesis, and the alternative says that the differences in the sample reflect differences in the population. To do the test, you just compare the observed frequencies with the expected frequencies. In this case, we are comparing, we'll have multiple variables. So an M by N table has M. So M might have two values by N, whatever N is. It has more values, maybe it could have just 2, 3, or more. Either one could have more than 2. So we're just looking at the simplest type here. And you can it's best to do the chi-square I mean, depending on the structure of your data, there's some special qualifications, is what I'm getting at, that go into doing a 2x2 chi-square here, and a correction that you should use. I'm not going to get into that. We're not going to discuss that. Just be aware that they're there. Depending on what you're interested in, you could, depending on the outcome, you should make sure you're making a correct choice if you have a 2x2 to do a chi-square or a z-test. But this is what we're talking about with the test of independence. It's telling you is the variable m independent from n. And the process for getting for doing the statistic is the same. We use a slightly different process for computing the observed and expected values, but they still are based on the overall number of observations and distributing them evenly across the groups based on the observed for the row. In summary, the real take-home messages here are that the z-statistic can be used in 3 primary ways: to test the hypothesis the data were generated according to a chance model, a particular chance model, and when the model is fully specified, the degrees of freedom are just the number of terms minus 1. The significance level gives the chance of the model producing observed frequencies as far from the expected frequencies or even farther, and the distance can be measured by the chi-square. So the chi-square can tell us how far away, it can give us a measure of how far the observed were from the expected values. The problem is to decide, the next type of test is when we use the chi-square statistic to tell us whether the data have been fudged to make observed frequencies closer to the expected frequencies. If the data has been manipulated in some way, the chi-square test can help you see that. And we can use the chi-square statistic to test for independence. We can only do the chi-square test for independence when the data have been obtained from a simple random sample and an inference about the population is wanted. In terms of the dependence or independence of the variables in the population. It's what we find out when we do a chi-square statistic for independence. The basic structure of the chi-square test is the same across these tests, though. There are some slight nuances in how you interpret your statistic. In the case of our hypothesis, our data manipulation test. And the test for independence, just had the difference there is with the calculation of the expected values. The chi-square statistic is a very useful statistic that you see often when in articles accompanied with these other statistics that we've discussed, and it helps to, it is often used, as we saw here, to help investigators look at to test their model. And that's a very common practice. Remember that the chi-square test is for categorical data when you have the frequencies and 3 or more groups. And that's the final chi-square attack. Just remember to look at what type of what your variables are measuring. and that'll be a helpful guide in using the chi-square statistic.